Hello and welcome to physics. So this is our first lecture, and the cover slide here, I put a copy of the textbook on it. It's the fifth edition is the one we're using, and I think by now you probably already have purchased it. It should be listed in the bookstore as the text of choice. If you got version 4, the difference is that the problems in the back of the book and a lot of the examples within the text are different. And some of them contain a lot of errors, or quite a few errors there, that were fixed in the fifth edition. So it is really important that you use the fifth edition. The Mastering Physics comes with an access code, and you would get the latest edition or fifth edition as the electronic copy with Mastering Physics. So the first chapter is our introductory chapter, and basically our definition or physics defined is that physics is the study of the fundamental laws of nature. So that's a pretty broad topic or pretty broad definition, and rightfully so. The laws of nature underline all physical phenomena in the universe. So it's the laws of gravity are an obvious one, but the laws of motion. Every type of motion, not just planetary motion, but the motion that we're going to solve, that we're going to focus on a lot of. It's physical motion of humans and cars and things like that we're familiar with in everyday life. And then the laws of motion or the laws of nature also, of course, govern ideal gases and the ideal gas law. And a lot of the things that we cover the second semester, like electricity and magnetism and optics. So pretty much physics, both semesters of physics, we're going to be studying the fundamental laws of nature, and we're going to see how physics applies to everything. So as you progress through the semester, keep an eye out for as you're walking around or things that you're doing, keep an eye out for how you're applying the concepts of physics. And as we go through the chapters, each chapter, you'll be able to see physics more and more in your everyday surroundings. So these physical laws of nature, they're expressed to us in a sentence like a regular law would be, but they're also expressed by equations, and those equations they show the laws or they express the laws in a mathematical form, and they show the relationships between all of the components of that law. So rarely is there ever a law that doesn't have a relationship to it. So pretty much every one of our laws are going to show things like a cause and effect. If you have one parameter, what happens to another one. So force is a good example. When you apply a force to something, you consequently have a mass. You have some kind of an object, and that object has a mass to it. So when you apply a force to that mass, the resultant action is acceleration. So that's one of our laws of physics that we're going to do in chapter 4. We're going to see that our famous equation F equals ma. So we apply a force to an object. The object has mass, and it causes an acceleration. So for this chapter, you don't need that, but we will learn that in actually chapter 5. I said chapter 4, but we actually get to that in chapter 5. But that's one example of where an equation expresses the law mathematically, but then it shows also the relationships between components of the equation, but also components of the law too. And so as we progress through the chapter or through the semester, through the whole year really, every time we get to a law or a equation, we're going to work on those relationships, because those relationships between the components are oftentimes an MCAT test, and they'll ask things like, particularly with volumes and areas, when you change a parameter in one of those equations, what happens to the other? So if you increase force on the same object, you're going to increase the acceleration. So that's a direct relationship. It's directly proportional. But then on the other hand, if we solved for acceleration, if we did that, if we took our equation again, we had F equals ma. But if we also wrote it as A equals F over M, then then when you have that, you still see the direct proportionality there. But if you increase the mass down here, then you're going to decrease the acceleration. So they're inversely proportional. A and M are inversely proportional. But we'll go through that, of course, again when we get to those chapters or those relationships. But it's those kind of things we're going to work on all year long. All year long, every equation that we get to, we are going to look at relationships so that you master the concepts of direct proportionality as well as indirect proportionality. So every presentation, every chapter, of course there's a cover slide, but then there's also this overview of the chapter. So this is your outline, and you should use this as a study guide. So when you're studying, you should be able to go through each one of these bullets, each one of these lists, and you should be able to say what they are, like what are the units of length, mass, and time, what is dimensional analysis, and make sure you know how to solve dimensional analysis. Significant figures, that is the biggest area that students lose points on year after year after year. And what happens is that I solve the problems for you in class and in the lecture, so you're going to see that today. And a lot of times I put the answer down, and I purposefully put the incorrect significant figures, and then I ask the class, what's wrong with it? And people don't take notes. The students oftentimes don't write down what the answer is. They just write down what I have, and they tune out the rest of the discussion, and then consequently on the exam, they write the wrong number. They write the wrong or incorrect significant figures down because that's what's on the solution sheet. And so my point is that when we're solving problems here, make sure you listen to the entire problem and you go through the whole analysis too. And realize that make sure you understand the significant figures. That's really critical, and we'll see why in a little bit. So again, this slide right here is your outline, and you can use that as your study guide too. Make sure you know all the different things that we cover. So there's one thing here that I'm going to cross out, and it's order of magnitude. So your textbook, so I have the word skip right there. So your textbook is going to cover it. And quite frequently in the later chapters, they'll have an order of magnitude calculation. And the reason we're going to skip it is because you are going to be a doctor, and precision is absolutely critical. If you do an order of magnitude calculation, and that's a rough estimate, that's all it is. You're not giving a precise amount. You didn't calculate the precise dosage that the patient needs. You just gave a rough order of magnitude, an order of magnitude calculation. It's a rough estimate. Well, obviously, if you give the wrong dose, you can hurt the patient. So a lot of times people say, well, there's other people, the pharmacist will catch it and things like that. Well, no, that's not always true. The pharmacist, there's quite a lot of times where the pharmacist makes mistakes. They're supposed to compound something and they don't, and consequently, the patient gets an overdose. There's tons of stories where people make mistakes, and that's fine. We're all human. Everybody's bound to make mistakes. So the point here is you want to minimize the mistakes that you make when you are a doctor, because you're the one that is going to pay for the malpractice insurance, and you're the one that's going to get sued. So you want to make sure you have all your ducks in line and all your calculations are accurate. So we're not going to even bother studying order of magnitude or figuring out how to do it, because you want to make sure that your calculations are always accurate. Anytime you report a number, you want to make sure that it's an accurate calculation and that it has its accurate significant figures there, and that you have the correct units there, and then of course the correct instructions for how to take the medicine or whatever it may be. So we're going to skip order of magnitude. So when you're reading your textbook, feel free to skip over that part as well. So our measurements, that's going to be our first part. our first part of our chapter. So our measurements are really, accuracy is incredibly, here, I hope you can see that. I didn't mean to cover that up there. So accuracy is essential. So aside from the part that we just mentioned about the malpractice insurance and being sued, things like that, even aside from that, the accuracy is essential because you're treating a patient and you want to make sure that in this particular example, it's radiation oncology. So the patients in both pictures are receiving radiation, presumably for a tumor. So you want the patient positioned accurately and the machine parameters all set accurately. You want the positions set correctly, the patient position and the machine positions. You want all the settings in the machine to be correct and set correctly. And you also want the calibration to be set up, and you want the latest, you want it to be fully calibrated. And then you also want to record how you took the measurements. So you have to record all of your data, even if you're not a radiation oncologist. I mean, granted, radiation oncology is probably the extremes of the data collection, because you'll have a radiation treatment plan that specifies all of these, all of the data, and you can't move forward without it. So there's some good controls or safety controls and things like that that would prevent moving forward with the treatment if you didn't have that radiation plan developed and accurate. And because obviously radiation, you could really hurt someone with it. So the radiation plan is very detailed and has a lot of data in it. And it has to be repeatable. A patient undergoing radiation will go typically will go 5 days a week to receive the radiation. So when they're going 5 days a week for 30 days, every one of those days, there may be a different tech on certain days. So the person setting up the machinery and helping you get in the position, or helping the patient get in the position, that person has to be able to repeat everything in that plan. They have to be able to set it up exactly. So every day the patient gets the exact same treatment in the exact same spot, the exact same location, the exact same room. Everything has to be absolutely 100% repeatable. So of course the radiation oncology or radiation plan is detailed. But then if you don't want to go in the radiation oncology, whatever field you do go into, you're most likely going to have to work with Epic. So you're going to have to enter data every time you see a patient. You're going to have to keep a record of what happened, what you talked to the patient about, what your recommendations were, what you prescribed. A lot of it is kind of point and click, where you go through all the lists of ailments and check off what they have. But then there's a lot of discussion parts too, like everything that you recommend. You're going to have to go into a free-form text box and type your recommendations. So you want to be able to explain why you're recommending something. And you also want to, anything that involves a mole or a tumor or some physical aspect, you're going to end up having to document that, so that if the patient comes back, you'll be able to recall what you did. But if the patient returns and sees a different doctor, that doctor will know what you did as well. So it's really accurate. Measurements and data are very critical, as is the record keeping. So very critical to treating your patient with the highest amount of respect and the highest amount of accuracy as well. So here's an example, another example. So we have our radiation oncology. Well, here's radiology, and this picture is courtesy of Dr. Fenderson from Jefferson. He's a pathologist, but this is an image, a radiology image, a mammogram, and his point in talking about this picture is that when we look at the mammogram, we notice a mass there. So this patient has a mass. We don't want to call it cancer. We're not even sure we want to call it a tumor. And all we know is that we see an abnormality there, and it's the arrows are pointing right to that mass. But he notes here that it's a very dominant mass. It's very prevalent, and it has smooth borders. It's not like a web. It's not like a spider web with a lot of things, a lot of projections out of it. It's very smooth, and that typically indicates that the mass is a fibroadenoma. Well, a fibroadenoma is not cancerous. But you don't want to ever tell a patient that. You don't want to just to say, oh, well, we saw a mass. It has clear borders, so it's a fibroadenoma. You have nothing to worry about. You don't want to say that because you didn't biopsy it. So that's your data. Your data is the biopsy. And your data, for the most part, gives you certainty. And there of course, are some false indications there, depending on how it was done. But again, how that biopsy was done, you'll be able to read the doctor's notes to see how he or she conducted or did the biopsy. Was it a surgical biopsy? Was it a needle biopsy? If it was a needle biopsy, where did they insert the needle? If it was a surgical biopsy, where did they take the tissue out of? All those things help you know or pinpoint with accuracy what the outcome or what the results of the biopsy were. But with this picture here, what's troubling is even though Dr. Fenderson is clearly saying you must biopsy for certainty, unfortunately, a lot of doctors don't do that. My mother passed away from breast cancer for the reasons that we're looking at right here. The radiology center did the mammogram, and they sent her a letter saying everything looked fine. Come back in 6 months, because she was 76 at the time, and they said because of her age she should return every 6 months instead of every year. Well, unfortunately, it was a cancer. It was cancerous. She had breast cancer, and they never said anything. And at that time, this was she passed away 11 years ago, so she was diagnosed 16 years ago. And back then, the radiology reports that were sent to the doctors really didn't give the full report. They just summarized the findings. So the gynecologist got the report, and it just had a summary, the end result, that that everything was fine, nothing was noticed. But he didn't see, the gynecologist didn't see the data, didn't see anything at all about a mass being present. And then even the physical exam that he did indicated that, well, if the mammogram didn't show it, maybe a breast feeling lumpy, especially at her age. There were dimpling in the skin, and he missed all the signs. So like dimpling of the skin and inverted nipple are typically signs of breast cancer, and that's what my mom had. So unfortunately, when the mammogram came back saying everything was fine, the doctor overlooked all the other characteristics and did not ask for a second opinion, nor did that doctor ask to see the full report. So unfortunately, that tumor that my mom had, the cancer spread, and it spread to her bones. And she was putting soup in the microwave one day, and her clavicle snapped. And that was because those cancer cells migrated from the tumor that looked a heck of a lot like the one here. My mom's mammogram, the tumor looked more like a golf ball, perfectly round, whereas this one here in the picture looks a little more pear-shaped. So the cancer cells spread and latched onto her bones and were eating away at the bone. And that little bit of pressure that when she lifted that bowl of soup to put it in the microwave, that little bit of pressure, because the cancer had eaten away at so much of the bone, that little bit of pressure right there snapped the rest of the remaining bone in half. And when she went to the doctor, the emergency room did a bone scan expecting to see osteoporosis, and instead it came back showing cancer. And fortunately, she lived a really good quality of life for another 5 years. But still, she probably would still be here. She had no heart trouble or no other issues at all. So she'd probably still be here. Hopefully, if they had actually treated that as a suspicious tumor and sent her for a biopsy. So of course we know that early detection is critical. So as soon as you see something like that, don't make an assumption. Again, accuracy of measurement. Just because you're eyeballing something and just because it may look indicative of a fibroadenoma or a calcification, it doesn't mean that it really is. Just because you're eyeballing something it doesn't make it accurate. Only the numbers, the data, is what makes it accurate. So make sure that you really commit yourself to collecting all the data that you could possibly collect from your patients, documenting it, and of course doing the appropriate analysis and appropriate follow-up with it. Here's another example of measurements. This one's from dermatology. And of course, we have a benign and malignant tumors here. This one here does pretty much always show benign, pretty much is always encapsulated. Malignant has these funny asymmetrical look to it. They're typically, again, like the fibroadenoma, these are typical patterns, but you don't know until you biopsy. And there's a lot of debate in dermatology back and forth as to whether the moles should be removed and whether they should be biopsied. Some people have a lot of benign moles on their body, and would they want every one of them taken off? I don't know anybody that says no, just because of the possibility that it might be cancer. So I don't know why there's still so much debate back and forth when everybody always says get them off and figure out if it's cancer or not. So here with the measurements, the other part of it, aside from the symmetrical or asymmetrical nature of the moles right here, the other part is measuring where those where they're at. And, so if you saw these moles on a patient and you removed it, you're going to tell the patient to come back in a couple of weeks, maybe a week or 2 weeks, for a follow-up visit. And when they come back for that follow-up visit, you got to remember what you did to the patient the last time you saw them. So that's when you go back to your record, and if you just say you removed the mole, well, where'd you move it? Where'd you remove it from? What part of the body was it on? Well, if you just say you removed it from the shoulder, all right, which one? Of course, you probably would have already said the left or right shoulder, but how far was it from the neck? Where exactly on that shoulder was that mole? And where would you be looking at? So that's where your anatomical planes come in. And this is something, if you've already taken anatomy and physiology, you know this stuff inside and out. If you have not taken anatomy and physiology yet, you will learn this, and you will. These will be second nature to you because you're going to use them all the time in medicine. So even though in physics, this is the last time that we'll see, the one and only time that we'll see anatomical planes, the point that I want to make here with reference to those moles is that when you pull something off the shoulder right there, well, if you don't take a measurement, you're still going to be eyeballing. So you would want to take your ruler out, your little tape measure, and you want to measure right from that sagittal, right from the median line, right on over to that mole there. And maybe you're going to do, maybe you're going to start from the edge of the clavicle. I think it's from the clavicle at the acromial part. I forget which end is the median part, but you're going to find some landmark that maybe on the clavicle or whatever's closest to that median, and then you're going to take that measurement on out, so that when you come back, when the patient comes back to you, you can look in that same area again to see if the mole regrew, if the removal, if there was any. If it got infected after, if the wound got infected afterwards. So you're going to impose. You're going to take these anatomical planes, and then you're going to impose a measuring stick, basically a ruler, where you're going to use these anatomical planes as your references, and you're going to find your reference points and then make your measurement there. Similarly, too, if it was a mole in the chest. And we know a lot of guys get moles on the chest because there are a lot of guys that were lifeguards, or beach lovers. They're down the beach all the time and they're not wearing shirts. And consequently, all that sun, if they're not putting sunscreen on, they're more than likely, highly likely, to start getting some moles. And so, of course, again, wherever that spot is, you want to pick your designation and make that measurement. And then, of course, record it. And when they come back, you want to repeat your results. So even though you don't need a treatment plan here like you would for radiation oncology, you still need to make measurements. You still need to have everything measured out, and your frame of reference, so that when your patients return, you can remember what you did to them, and then be able to verify that everything is still okay, or whether, or maybe perhaps needing some other treatment. So our units of length, units are very important. The length, mass, and time are basically the building blocks of physics, and are the physical quantities that we're going to keep using an awful lot in physics. We're going to, especially the first semester, length, mass, and time are very critical for this whole semester, and you'll understand why when we get to the next chapter. But these are the building blocks of physics, and so length is always going to be denoted by the letter L, and then mass is m. Oftentimes the mass is a lowercase m, and then time is usually a lowercase t, except for in chapter 14 where we get to periodicity, and then you'll see the capital T, and then. The other building blocks of physics, of course, the first three, length, mass, and time. Force is a very important one. We're going to see that that's a foundational concept that carries through the entire year. Velocity is another measure for speed. The whole first semester, we're studying motion. So when we study motion, we're always going to be talking about velocity. And then at the end of the semester, chapter 15, we get into density, and we'll see that becomes a fundamental concept too that carries forward in the next semester. And then resistivity, that we're not going to look at this semester. That comes in next semester in electricity and magnetism. And then temperature also is oftentimes a lowercase t, except some of the laws, some of the thermodynamic laws that actually do use a capital T there. But even though it sounds confusing between T for time and temperature as well, you'll know by the rest of the equation, the other parameters that are related to it. You'll know instinctively. You don't have to worry about messing something up, or not being able to distinguish. Are they asking for time or are they asking for temperature? It'll be abundantly obvious which one they're asking for. And then luminous intensity, when we study optics in the spring, we'll get to this. And then magnetic field strength, same with electric field strength. We'll study both of those in electricity and magnetism in the spring. So these are our fundamental building blocks, and then and they're the units or things that we're always going to be measuring. And then standards, we're always going to follow standards. We're not going to make up our own measurements or measuring standards. We're going to use the international standards, and so they're standards, which means they have which means there's terms that have they are terms that have specific meaning in physics and a very precise way of measuring them. So that precise way of measuring them, that's what you're going to carry forward to the medical practice, especially if you want to go into dermatology. When you're going to be able to combine that with those anatomical planes to have a very precise way of making measurements when it comes down to treating a patient where measurement becomes critical. So our units of length, mass, and time, the SI units, International Standard of Units. So periodically or quite frequently, especially in the beginning lectures, you'll see this MCAT alert. So this slide, why it's important, again, is accuracy of measurement is very important in medicine. So you can expect to see some MCAT questions where you're going to have to use measurements. There may not be a question directly saying what's the unit for length, but you're going to need to know the unit to pick the right answer. I mean, they may give you the correct number, but an incorrect unit. So that's where you're going to have to know what the units are. On Canvas, I posted a mapping of all the MCAT topics in physics. So everything, their study guide or outline when they say these are all the things that you need to know in physics in order to prepare for the MCAT, well, I mapped all of those to our lectures. So you're going to see that every one of our lectures, except chapter 12, which is planetary gravity, that part's not on the MCAT, but all our other chapters cover topics that are on the MCAT. I do want to be really clear to say that the physics class is not an MCAT prep class, nor is any program in the P4 program. The reason is, again, that to get into medical school, you have to have taken an undergrad level physics course and bio course, things like that. So these are meeting the undergraduate requirements. And it just happens that it's extensive enough, our courses are extensive enough and detailed enough that we're covering, it is good, it helps you as a secondary benefit prepare for the MCAT. So you're going to learn everything that's on the MCAT. You are going to learn it here in the P4 program, and then some. You're going to get quite a good background here. So our International Standard of Units is what we're using here in physics, and for length, that's the meter, and then the mass is the kilogram. So that's one thing you want to keep in mind. Mass is not the gram, so it's different than length, where length is the main unit of meter. And then you have millimeter, centimeter, decimeter, all the different forms. But with mass, it's actually literally the kilogram, not the gram. So you want to keep that in mind. And then time, of course, is the second, is the unit there. So under each of those bullets, you can see what the standard is, how they got to, or how they arrived at mass being a kilogram, so, or what it really means. So 1 kilogram is the mass of a particular platinum iridium cylinder that's kept at the International Bureau of Weights and Standards in France. So it's about slightly more than a quart of milk. But your textbook has a whole overview of how they arrived at the standards and all of that. You can read it if you want to, but that's not testable information. The only thing that is testable in this class and probably the MCAT is the actual units, the top part of the bullet. So that this is really what you got to know, that the length and mass and time, those 3 lines right there are what you want to know. So there's a total of 7 base units. So we went over some of them already. So length, time, and mass are the first ones. But these base units, length, time, and mass, are the things that we're measuring, not necessarily the units themselves. So the unit of length is the meter. So these units on this slide right here, there's 7 base units. So that's the baseline. That's really your lowest level right there, your fundamental level. And it's the meter, second, and kilogram. And then ampere, which measures current. So that's the base unit in electricity. Degrees Kelvin is the base unit in when you're measuring temperature. And then the candela for luminous intensity, and mole for the amount of a substance. So all of those 7 units right there are your baseline. And then all the other units that we use in physics they're all going to derive from these seven units. So speed and velocity, we'll see that velocity is a vector and speed is the magnitude. So both of the magnitude of velocity. So both of those have units of meter per second. So that's what we had. That's what we're showing right here. So our meter per second right there is our unit for speed and velocity. So you can see that it's made up of meter and second right there. It's a combination of the two right there. And then a watt is a joule per second, which is meter squared. The software package I'm using right now is called Explain Everything, and it doesn't always treat the super and subscripts kindly, so it often takes them out. So the watt is a joule per second, and a joule is a meter squared times kilogram divided by seconds cubed. And s to the negative 3 is that's an inverted. It means 1 over s cubed. So you can see there that meter, kilogram, and second is right up here. There are 3 units that make up the joule. So all of our base units are often used in combination to make up another unit. So all of the other units end up deriving from the 7 base units. So here's a slide that it's a huge MCAT alert, and it's also a huge class alert for this one too. So you want to know this chart. You want to memorize this chart. You want to know it so bad. You're going to commit it to memory, and you're never going to forget it. You want to commit it to memory and be able to recall it like you can spell your own name. That's how bad you want to know this chart. So it's very important because oftentimes it's a source of error when you're mixing compounds or you're doing something where you have different units. And so one example is really the one right down here where we have 44.7, and then again this is times 10 to the third. Times 10 to the third nanometer, or 10 to the third, well, even if we did 100, well, it wouldn't come out as 44, but this is 10 to the third, and this is 10 to the negative 9. So this unit, the 44.7, there's no units associated with that. We can assume it's meter, and it's going to multiply the 10 to the third nanometers. So 10 to the third nanometer is actually 10 to the third times 10 to the negative 9. See, we have nano right here, 10 to the negative 9, and it's indicated by an M. So we have 10 to the third nanometers, which is 10 to the third times 10 to the negative 9. So when you have powers like that and you multiply them, the 3 and the 9 you add together. So 3 plus a negative 9 gives you this negative 6 right there. So you wind up with 44.7 times 10 to the negative 6. And that negative 6 is a micrometer, micro. And that's right there. Your 10 to the negative 6 is micro. And we know we're dealing in meters. So you have 44.7 micrometers, or 44.7 times 10 to the negative 6 meters. So that's why you want to commit this to memory, because you don't want to inadvertently miss the fact that this problem right here has nanometers instead of meters. So we want to remember that meter is our fundamental unit. So it's okay if everything's in nanometers to report the answer in nanometers. But if you have disparate units, if you're talking about micrometers and centimeters, convert everything over to meter. Convert them all over, and or convert one, solve the answer, and then particularly or hopefully put it in meter as well. So again, you want to commit this to memory, and then you also want to pay attention to the capitals. The first 4 in this list are the only ones that are capitalized. Everything else are lowercase letter, or in this case, it's a Greek letter. So that's what you have right here. So you have the megameters in play here. You have 0.0332 times 10 to the 6th meters. So that's what you have here. This should be 10 to the 6th meters. And then consequently, you get this answer right here. So yeah, you want to make sure you know this chart, and you want to make sure that you recognize when you're reading the problem statement, you recognize the units and know how to treat them accordingly. You want to get everything over to meters, and or in a last resort, you could still put it as a fraction of a meter, like we have down here with micrometer. So again, commit this chart to memory for both the class and the MCAT. Your exams are on ExamSoft, but the more you know this chart, the faster you'll get through the problem solving on the exams. So here's a type of problem solving that we don't want to ignore. We're going to ignore the order of magnitude, but dimensional analysis is really critical, and it is an MCAT alert. So any valid physical formula For that formula to be valid, it has to be dimensionally consistent. So each of the terms have to have the same dimension. You can't add apples and oranges. I mean, one would argue, I think one class a few years ago said technically you can. You can put them in a blender and make a smoothie out of it, or you can put the apples and oranges in a fruit bowl and eat a fruit salad with it. So I changed the oranges over to knives, for this one. So our apples and knives are so drastically different, you would not be eating the two of them, or you wouldn't put the both of them together to make a smoothie out of it. So you can't combine things that are so drastically different. So a formula, all the parameters in that formula have to be dimensionally consistent. They have to have the same dimension. And dimension refers to the type of the quantity. It doesn't refer to how much of it. It just refers to the type of the quantity. So distance is measured in cubits, and it's also measured in meters, but its dimension is the same. Its dimension, regardless of whether the unit is cubits or meters, we're still talking about length. So distance is how far did you go? How far did you go from your room to the bathroom? And so if you measure from your room, from your bedroom to your bathroom, that's a distance that you traversed, but it's also a length. You could take a ruler out and you can measure the length. You can measure how far it is you walked from the bedroom to the bathroom. So you're measuring length. Length is distance. So the dimension there is length. The unit is cubits and meters, but again the dimension is length there. So when you do combine parameters, if we took a look down here, distance and time are two different things. So you're not going to add distance and time, but you can measure distance or length over time. You could. That's what you do with a car. When you're driving 35 miles per hour, you're measuring the miles in a time frame there. So you're not adding them. You're not adding them together. You're just setting a time interval by which you're going to measure that actual length or that actual distance. So again, that's really a key thing to keep in mind there is dimensions. The dimensional analysis has to be a valid one. So if we looked at this table here and we see that distance is length, but then if we want to calculate, or in order to calculate distance with a car, it's your velocity times time. So your velocity is length over time, and then so that's what we're going to put right here. We're going to put velocity is length over time. So this is velocity times time, and that's t. So these t's are crossing out, and you get L. So actually, let me make that a little neater for you. So a distance again is velocity times time. So distance is length. Velocity is length over time. So we got that right here. We got our distance and our velocity, and then time is the capital T. So when we multiply velocity times time, the time component drops out, and we get L equals L. So that's distance equals distance, or length equals length. So that's dimensionally consistent. It's a valid equation then because it's dimensionally consistent. We're not saying that length equals time. We know that they don't. They're two different. Time is a completely different quantity, a completely different dimension than length is. So that would not be a true. If we said L equals T, that's not a valid equation. If we say L is not equal to T, then it is a valid equation. They are totally different. So we could do the same with velocity equals acceleration times time. So velocity is our length over time, and it's equal to our acceleration, length over time squared, times time. So here, this T crosses out, and it erases away that power there. And we see we have the same thing on each side of the equation. We have a balanced equation. So what's on this side equals what's on that side, and that's the correct statement there. So that equation right here, velocity equals acceleration times time, is a valid equation. It's a valid relationship. So do you see the relationship with the info in the chart for velocity? So let's take a look at that again. So we have our velocity. I'm sorry, we'll take a look at it, not again, different perspective here. So we have our velocity is length over time equals acceleration, length over time squared, times time. So the time cancels out and we get L over T equals L over T. So we're going to see coming up that velocity is a derivative, acceleration. When you derive acceleration, you get velocity. So, and then when you derive velocity, you get distance. So we'll see a little bit more of the math involved there as well. And then the last part there, energy equals mass times velocity squared. So that's right here. That's this part right here. Energy equals our mass times our velocity squared, L over T squared. So that gives you L squared over T squared. So energy is mass times velocity. So energy is a mass in motion, another way of saying that. So our dimensional analysis, a little bit more on that. So we just briefly started. For dimensional analysis, you want to use this table 1-5. So our dimensional analysis, we always, for the most part, we'll have an equation, and we want to find out if the equation is a valid equation. Is it true? So we're going to do a dimensional analysis on it. And so we start out with our length, mass, and time with those units. And our first equation is x equals half vt squared. So before we move on, you need to know what x is. And x is your position. So we're always going to say, we're always going to start with a position, and then we're going to end at another position. So you're going to walk from your bedroom to your bathroom. So in your bedroom, that's your first position. And then in the bathroom, that's your second position. And then you're going to subtract the two. You're going to find the difference between the two. And that difference is x2 minus x1, that delta x. Well, that distance from your bedroom to your bathroom, it's a distance and it's measured in length. It's measured in units, the units of length. So your distance is your length right there. So x will be our position or difference, and it'll be our length. And then the half is a scalar. So the half has... that only changes the amount that you have. It doesn't change what you have. It just changes the amount. So the half, the scalar value, that can be ignored. So then we go over to velocity, and that's length over time. And then time is of course, our capital T, and that's squared. So the capital T, this squared part drops out, and so does that. So we wind up with L equals LT. Well, L doesn't equal LT. L equals L. So in that case here, this is not a dimensionally consistent. It's not a dimensionally correct equation. So x equals half vt squared is not a valid equation. It's not dimensionally correct, and it's not valid. So you would never want to use that to solve for x, because you'll wind up with an error. But then this one here. So this one here, is this one dimensionally correct? So x again is distance or position, and it's measured in length. So we put our L there, and whenever we're doing a dimensional analysis, we always put the brackets around our values, and it just helps kind of keep everything parsed together. And then we see that velocity is length over time, and then time, of course, is time. Now here the times cancel out, and we get L equals L. So that's a valid statement, and consequently the equation is dimensionally correct or dimensionally consistent. Saying dimensionally correct or dimensionally consistent, they're the same thing. They both mean the same thing. So here's our first problem, and it's a dimensional analysis. It's number 5. In your textbook. So which of the following equations are dimensionally consistent? So if we start with A, our first one, x is our length. So for A, we get our length And then the half, we can ignore that, or you can write it down if you want. But I would say ignore it because you don't want to you don't want to get well, actually let me put it here and then I'll show you what happens. So we got our half, and then our is our length. That A is acceleration, by the way, over t squared times t squared. So that should be a squared right there. So we wind up with the t squareds dropping out, and we get A equals half. I'm sorry, we get L. So our dimensional analysis is this L. So actually, let me change this right here. So we're solving for part A, or we could put it that way. So we get L equals half L. So is it dimensionally consistent? Most people go say no because of that half. Well, that's not correct. The half is a scalar, so you can ignore the scalar. You're saying you have a certain quantity of meters equals half that meter right there. So you have an unknown number of meters equals half of the unknown number of meters. And again, half is a quantity. It doesn't matter how much of it you have. What matters is, are you talking about the same thing? You have meters over here and you have meters over here. So you're talking about the same thing. You have meters on both sides. If we said seconds equals half a meter, well, no, seconds is time and meters is distance. So it doesn't matter what the scalar is. That can be ignored because it's just that's referencing or referring to an amount of what you an amount of what you have. But we don't care about the amount. All we care about is whether or not the equation itself is dimensionally consistent, and scalars don't have any effect on it. Scalars just affect how much of something you have. So so scalar affects how much of something you have. It doesn't affect what you have. It doesn't affect that you have units. It doesn't affect that you have meters. You still have meters if you reduce the quantity by half. So it's kind of like 9 meters equal, or let me put 8, that's easier. 8 equals half, 8 meters equals 8 meters right there, and you can get 4 right there. So the scalar part, again, it doesn't have anything to do with the meter part. It's just telling you how much of something you have again. So for part B, time equals velocity over x. So time is, you can either leave it in time, or you could put the units of s there, and then our velocity divided by our position. So our velocity is meters per second, and we can put our brackets around them. Times and now x is, you could either put the m down here, or you could say 1 over m. So because speed per distance, that hash line, it would be read as per, like meters per second, or speed versus speed per time. So here in this case, the meters cancel out, and I shouldn't have erased that. You have meters and meters, and here they cancel out. So you end up with s equals 1 over s, or time equals 1 over time. Time equals the inverse of time. Well, that's not true. Inverse time is a completely different metric. It's a completely different measurement. So it's not the same. That's not dimensionally consistent. So this one is dimensionally consistent. This one is not dimensionally consistent because time and 1 over time are two different things, two different measurements. And then our last one here is time again equals 2x over a, or 2 times distance divided by acceleration, and it's the square root. Well, the square root's an operator, so so the operator, you do want to take that into account. The scalar you don't care about, so you want to put here, so you could do your you can do your 2x over a. You can leave the 2 off if you want it, and then for this one here, you wind up with when we put our units in, if we want to say seconds equals meters divided by meters per second squared for acceleration, and then you wind up with s equals square root of s squared equals s. So you get s equals s. So yes, this is dimensionally consistent. And then this one here is similar type logic here. We want to do the same thing. So x over v is, x is our distance, so that's our L, or length, and velocity is length over time. And that we can rearrange that here. So this one we're going to invert and multiply here. So we get our L's cancel each other out, and we get time. So yes, this one does have the dimensions of time. X over v has the dimension of time. So we have yes right here. And then our acceleration over velocity is equal to L divided by time squared. So that's distance versus time squared. And then our velocity is distance versus, or distance over time. And we can rearrange that to our 1 over t. We want t times t, so that's our t squared. And then our 1 over t. And then we can invert up here, and we got t over t times t. So one of them cancels out, and we get 1 over t. So again, 1 over t is not the same as t. So this is a no, it's not dimensionally consistent. And so I'm going to erase some of this. Get our next little, get a little bit more room for our other. So our next two here, C and D. So 2x over a, the square root. So square root of 2x over a is and 2x over a. So 2x over a, that's going to be, we don't have to put the 2 in there. So x is length, distance is length, acceleration is length over time. And then we get, we end up with this square root of 1 over t squared. And that gives us the square root of t squared, and that equals t. So yes, that is the dimension of time right there. And then the last part right there, or last one's v squared divided by a, and v squared is L divided by t, and that whole thing is squared, divided by a, which is L over t squared. So this will give us L squared over t squared divided by L over t squared. And then when we invert this, we get t squared over L. So these cancel out, and that one cancels out. We get L right here. So so that equation does not have the dimensions of time. It has the dimensions of length or distance. So significant figures, as I mentioned earlier, big area that everybody loses points on. Actually this, now that you're online, your exams are going to be on ExamSoft, and they're all going to be multiple choice. So you're not going to have to write out you're going to have to solve problems, but then you have 4 choices, and I'm going to make the answers the choices. You can expect to see an answer, like suppose the answer is 0.13 meters. So you can expect to see of your four choices 0.13 meters, that'll be the correct one, but you'll also see 0.131, 0.139, 0.14 if maybe the answer gets rounded. So you're going to have to make sure you know your significant figures so that you pick the correct answer on the exam. So the accuracy of our measurements is limited based on the level of detail that's provided by the instrument you're using when you make that measurement. So most of your measurements when you're practicing medicine, all your instruments are all the medical instruments that you're going to use. We saw the radiation machine and the mammogram, but you're going to have a lot of other tools at your disposal too. And the accuracy of that instrument is what's called the resolution. How well can it resolve the image you're looking at or whatever it may be. The accuracy of that instrument is its resolution. And the resolution determines the decimal position and the value of that last significant figure of the measurement. So typically a resolution is 1/10 the smallest division on the instrument. And what that looks like here, when we say 1/10 the smallest division on there, we see a ruler right here. And we see that if your instrument's a meter stick, the smallest division is 1/10 of a centimeter. So it's measuring centimeters, but your resolution is 1/10 the smallest division on that instrument. So 1/10 of that smallest division, 1/10 of the centimeter, and it gives you 0.01 centimeters. And so the last digit of measurement taken with a meter stick is going to be to that hundredths place. So the arrow is between 6.2 and 6.3. So you can estimate, you can give an estimated measurement of 6.27 centimeters, and it has three significant figures. So we're saying estimated here, and you're probably saying, well, she just got done saying we're ignoring order of magnitude. Well, I did say that, and we're not contradicting that right here. An estimated measurement or an eyeball measurement when you have a meter stick, you still have to take that measurement. You can't avoid it. So when you're measuring with your, when you're measuring where a mole is, you're going to say in your report that you used a meter stick. So when you say that, everybody knows that a meter stick is accurate to 1/10 the smallest division, and that a meter stick is going to have centimeter. The smallest division on a meter stick is a centimeter. So when you put the when you make that measurement there, you're going to be able to, you're going to report it just like you see right here, where you're going to say that when you made your measurement, you're going to use a little pen or something to see that really kind of really falls right between those two numbers there. So you're going to report in, and you're going to type into Epic that when you measure the mole on the patient, it was between 6.2 and 6.3 centimeters from the median. So you can say then, when you say this part, between 6.2 and 6.3 centimeters from the median, you can then go on to say that you're estimating a 6.27, and you don't have to say three significant figures, but that's just implied, knowing that the centimeter is the smallest unit of measurement. And we see our three figures right here. We see our three our significant figures, that at this point, the three significant figures, or the three positions. We see three positions for sig figs. So we have three positions right there. And so that's where you want your accuracy again in your answers as well. You can't get, because of the ruler and the limitations of that ruler, the best and most accurate you can get is the arrow between 6.2 and 6.3. So you have to be able to answer that in some way. So your answer again is to literally say the measurement fell between 6.2 centimeters and 6.3 centimeters. So the estimated measure is roughly 6.27, and so you're reporting the accurate number of sig figs, and you're also accurately reporting the context in which you took that measurement. So the sig figs, the rule of thumb for multiplication and division, is the number of sig figs is equal to the number of significant figures in the least accurately known quantity. So that's a really important thing there too. In the last example, we only had one one measurement and one instrument, but you may have multiple instruments you're using. So an example is speed equals distance over time, where we have distance in centimeters and time in seconds. So 21.2 centimeters divided by 8.5 seconds, that's your distance over time. So your speed is going to be, it's going to give you 2.5 centimeters per second. We know we go by meters per second, so you're going to want to calculate that, but or convert it over to meter. But for the sake of this example here, when we do our 21.2 divided by 8.5, when we calculate it by hand, we get 2.5 centimeters per second. But on the calculator, we get that real long number. We know that long number is not accurate because our stopwatch and our reading and our ruler gave readings in the tenths. So our final answer must also be in the tenths. We're going to use a ruler to measure distance and a stopwatch to measure the time. And both of them are accurate to a tenth. So that means your final answer must also be in the tenths. So just because your calculator gave you this real big answer right there, you don't want to report it. You want to demonstrate that you understand sig figs and the units or the tools that you used gave you centimeters and seconds, and that your significant figures are going to be governed by your significant figures are going to be governed by this one right there, because you can't give something more accurate than you already have. So the stopwatch and the ruler gave readings in the tenths. So again, your final answer, your tenths right here, your tenths. So your final answer has to also be in the tenths. So they're the things you definitely want to keep in mind when you're solving any of our physics problems here. So a little bit more on our sig figs. If one measuring device was precise to the hundredths and one to the tenths, you can only be as accurate as your least accurate tool. So that's what we said back here. We said the number of sig figs in the least accurately known quantity. So the least accurately known quantity is often going to be the smaller, or I shouldn't say smallest, but well, let's look at this example and then you'll see. So here we have one measurement is 16.74 seconds, and the next one's 5.1 seconds. So when you add them, the total's 21.8 instead of 21.84, because we have to report it in our least accurate, and our least accurate is this one. This one's more precise. It's got 2 more units there, 2 more digits there. So this one here is the least precise, and that's what we have to go by. If you report it, the number here, you're given greater accuracy to the instrument, and you cannot do that. Every instrument is made to a certain level of precision, so you have to respect that. You have to make sure you know what the precision is of all of your instruments. And if you're using multiple instruments to make a measurement or working on something where you get numbers, you got to report to the least accurate. Otherwise, you're giving accuracy to something. You're making it up is basically what you're doing. You're giving accuracy to something that doesn't deserve it. So make sure that you can't give greater accuracy to something that's already been manufactured to be accurate to a certain degree, to one level. So again, you want to make sure you report to the least accurate. So a rule of thumb for addition and subtraction is that the number of decimal places after addition or subtraction is equal to the smallest number of decimal places in any of the individual terms. And so that's what we saw right here. We have our 5.1 plus 21.8, and no, I'm sorry. Let me erase that here. So one measurement is 16.74, and the other's 5.1. So if we carried that 4 down there, that would not give us that's not accurate. So the number of decimal places after addition or subtraction is equal to the number of decimal places in the smallest of your terms. So the 5.1 is the least accurate. So we're going to report our answer with just one decimal, one number after the decimal. So our example right here is a parking lot, and we have the parking lot's a rectangle, and so let's just draw that out here. We have a rectangular parking lot, and we want to calculate the perimeter of the lot. So we know that it's 124.3 meters long and 41.06 meters wide. So we know that because we're talking about perimeter, this side's also 41.06, and this side here is 124.3. It's a perfect rectangle. So the perimeter is the sum of all the sides. So the perimeter is equal to the 124.3 meters plus 124.3 meters plus 41.06 meters plus 41.06 meters. So when you sum all that together, you get 330.72 meters. So is that accurate? So I hope you said no, because this one is our limiting. See, we reported it to this one. If we say 330.72, that's reporting to this level of accuracy. But the real level of accuracy is dictated by the 124.3. So we just drop that 2 off, and we report the 330.7 meters. And so the length has the least amount of significant digits in it. So I believe that's everything. Oh no, we have some sig fig rules here. So our sig fig rules are all non-zero numbers are significant. So again, all non-zero numbers are significant. Zeros between two non-zero digits are significant, but leading zeros are not. Trailing zeros are, even though leading zeros are not significant, trailing zeros are significant. So you can see the examples here. Trailing zeros in a whole number with the decimal are shown as 540 with that decimal. That's not a period right there. So that indicates the zero is significant. So what happens there, trailing zeros in a whole number with no decimal is not significant, because so if you look at these two numbers right here, one got real precise and put the decimal there, and the other is reporting 540. And we only would have two sig figs there, though. This rule is a little bit confusing. And the reason why you wouldn't consider that a significant figure, the trailing zero there, because is the measurement really accurate? Did you actually really measure it to 540? That seems like such a nice, neat number. Are you sure it wasn't 541.2? Something like that. So 540 raises the question: were you really that did it really just by coincidence fall so nice and neat on a tenth? Some 10th or 20th% there. So if did you actually get that measurement? And the reason or the answer is probably no. Most likely you got something around that number and rounded it, or either upper or lower. So when you see that, question whether they really did get that precise. And if they did get precise, they should know to write their number with the decimal after it. So that notation right there tells you, even if you don't put that zero, so this notation with the decimal says that you really did get that accurate. Your measurement really did fall on 540. You got 10 units and a whole bunch of subunits between 540 and 550 that it's hard to believe that the object would literally fall right on 540. But if you're certain it did, then put the decimal spot right after it to indicate that you really did get that, that you really were able to get that precise. So trailing zeros in a whole number with no decimal are not significant. So you would only have two sig figs in the 540. And then our scientific notation, when we look at it, like the bottom part there, only the 1 and the 2 were significant. And you can rate it as 1.2. You want to take this decimal right here, and move it. So you got 1, 2, 3, 4. So if you put the decimal there, you moved it 4 places this way. You move the decimal 4 places that way. So the number started out 0, you go 4 places that way, and you get this 10 to the negative 4. And then similarly, 6 sig figs here, the 1, 2, 2, 3, 0, 0. They're all your significant figures. So you can convert it to scientific notation by taking that, taking the decimal and moving it to the spot right there. So you're going to move it 3 places to the right, which means the number goes to the left. So let me clarify that. When I say the number goes to the left, basically right here, you have your 0.00012 times 10 to the 0. Well, 10 to the 0 equals 1. So if we put that right here, we're just multiplying the same number by 1. And when you multiply a number by 1, you don't change it. It just equals, it stays the same. So if we look at this right here as, let me put that back here. So we have this as 10 to the 0. So when you put it in scientific notation, the scientific notation, you always have one number to the left of the decimal, and then you could have a few numbers to the right. So you're going to move the decimal 1, 2, 3, 4, and you get your 1.2 times 10. So now you got to take this 0. Because you move the decimal that way, you're going to move the number to the negative, into the negative. You're going to move it 4 places negative, so that if you have this number now and you want to convert it to straight numerals, you're going to say 43210 that way, and which means you take this one 4 spots this way. So I'm sure that you know how to do this. If you do still have trouble with that, let me know and we can go over it a little more. So round off error is something else you want to keep in mind. So the last digit in a calculated number can vary on how it, depending on how you calculate it, because of round off error of insignificant digits. So here's an example. You purchase 2 items in 2 separate transactions. So you go to the store and you buy something, and then you just realize you forgot something and you get the other thing off the counter and buy that. So you have your 2 transactions, and they're both charged 8% sales tax. So you get this first, your calculator gives you this 2.3868. So you have your three significant figures there. And then your second item is $1.35, and you add your 8% sales tax to it, and you get your 1.458. And but you only want 3 significant figures, so you round it to 146. And then you add those 2 numbers together. You want to say, well, how much did I spend? So if you say how much did I spend, you add those 2 together and you get your 385. But then if you had purchased them, if you hadn't forgotten that you wanted that other item and you purchased them all in the same transaction, then when you do that here, you add the 2 together. The cashier adds the 2 together and gives you a total, and then the sales tax is calculated on the total, and you get 3.84 there. So you're off by a penny. So it's a good idea to keep an extra digit throughout your calculations, then round your final answer. So instead of rounding each of the individual calculations, get your final answer and then round that and calculate, do your sig figs in the end. So converting feet to meters, 1 meter is 3.281. So it would probably be a good idea to memorize that, but for the exam, you'll have an equation sheet, and the equation sheet usually has the conversion factors on it too. They always have the conversion factors. So you're going to be given that too, so you don't have to memorize it now. So our 1 meter equals 3.281. You can also represent it as the number 1 equals meters per feet, and that's really what we're doing there is we don't want to change when we're converting. We don't want to change the value of the number. It will get a different number, but we want them to be equal so that when we divide the two of them, you get the unit 1, you get unity. So multiplying by the conversion factor is the same as multiplying by the number 1. So that's why that's where we got right here, where we're setting our equation up to be 1 equals 1 meter divided by 3.281 feet. So different units, but these are equivalent. If you took 1 meter and you put a meter stick out, your meter stick might be this long, but then you took a big non-metric tape measure and you measured the same thing out right here, you could get this really long thing, but you're going to notice that right there, that 1 meter is the same as 3.281 feet. So they're the two. They're the same. They're the same value. So when you divide the two of them together, you get unity. So you have your two equal quantities right there. They're both the same length. So here, the 1 and 4 digits, you don't have to worry about sig figs there because it's a conversion factor. So here, your precision all the way out, your measuring precision, you got the two same lengths right there. So so your conversion factor is going to have a few more digits than your other. So when you're converting 316 feet over to meters or any number over to meters, you're going to take the number that's in feet and multiply it by meters per feet so that the feet cancel out and you wind up with meters in your answer. So the units cancel properly, and that's the key to converting correctly. The feet have to cancel out and you wind up with meters. So conversely, if you have meters and you're converting to feet, you don't do 1 meter divided by feet, you do feet divided by meters because you want the meters to cancel out. You have 26.4 meters equals how many feet. So the meter part in the bottom has to cancel out and you get feet in this answer right there. So they're dimensionally consistent because we're talking about distance in both cases. Remember that meters and feet are units. And they're units for the same quantity. They're units for distance. So we got distance right here, and we have distance right there. But our units are different. We just have meters and feet. So the units, that's fine. That's dimensionally consistent. The units can be different. We're still talking about both of those units, meters and feet, are still talking about length. We don't want meters and seconds because we're talking about distance and time. Here we're converting meters to feet. We're not converting at the time. That would not make sense. So you can have two units that both mean length. As long as they both mean length, you're correct in your converting factors right there. So again, if that didn't come out very clear, let me know. And we can go over that again. So an example here is express the speed limit of 65 miles an hour in terms of meters per second. So we still have speed, and it's in miles per hour, and so we're still talking about speed here, and we're talking about speed here, and we're talking about speed here. So again, both are speed, but the units are different, miles per hour or meters per second. So 5280 feet is equal to 1 mile, and 3600 seconds is equal to 1 hour. And 3.281 feet is equal to 1 meter. So we want miles per hour in the meters per second. So we have distance and time, distance and time. So length and time, length and time. We're both sides of the equation are the same dimension. So speed, we start out with our 65 miles per hour, and we want to convert it to meters per second. So miles per hour first goes to feet per mile, and then we have our hours per second there. So that's what these two ones are. This is equal to 1, and this is equal to 1. So our 65 miles per hour is getting multiplied by 1 and multiplied by 1 twice. So we're not changing. We're coming up with an equivalent number in feet per second instead of miles per hour. So again, we take our miles per hour and we multiply it by feet per mile and then hour per second. So the miles cancel out and the hours cancel out, and you wind up with feet per second. So again, you got to get rid of the miles per hour, the miles and hours in your overall equation. So to do that, you set it up first in terms of the inverse of miles. What's the how do we cancel the miles out? So that's converting it to feet, and then we got to cancel the hours out. So we have to convert that to seconds, and then we see that our miles cancel out and our hours cancel out. So our and then when we go the other way, 95 feet per second into meters per second. Is a little shorter here, 95 feet per second. We're going to convert feet to meters. And so the only thing that we have to cancel right there are the feet, and we get meters per second. So we go from feet per second to meters per second. The seconds we don't have to convert. If it said feet per hour, we would have to do some conversion, or meters per hour. We'd have to do a little multiplication there. But as written right there, we could just cancel the feet, and we got it in terms of meters per second. So converting units, here's another conversion. We write down what you know. If we had a word problem like this one here, we want to write down what we know and then what are we trying to get to. So 4.3 light years is the time it takes for light to travel the distance. So we know our equation of distance equals time times speed. So our distance is going to be 4.3 light years, but we have to convert it, we want to convert it to kilometers. So we start out with what we know, 4.3 years, and then the speed of light is 3 times 10 to the 8th. That didn't come out. That's 3 times 10 to the 8th. And so we have seconds in how many seconds in a year, and then because we want those years to drop out, and then we want our seconds to drop out, so we get 3 times 10 to the 8th meters per second is our speed of light. So the years cancel and the speed cancels, and then we still have to have those kilometers there, so we got to get rid of the meters. So how many meters are in a kilometer? It's 1,000. So the meters now drop out, and we wind up with kilometers as our answer. And we have and so 40 times 10 to the 12th kilometers, which is 40 pentameters. So scalars and vectors, we already mentioned scalars once. A scalar is just a number. So when we had those numbers in our dimensional analysis, we don't have to worry about them. They don't affect the dimensional analysis. But when we start in our next chapter, we definitely have to worry about scalars. They tell us how much of something we have. So there are physical quantities, and that's one physical quantity. A vector is the other physical quantity. So the scalar is the number and the corresponding unit. 1 meter is an example, or it could be negative. It could be negative 4 meters. So it's a number and a unit is a scalar. And remember that the unit is a measure of the dimension. It's not the dimension itself. So 1 meter, 10 feet, 1 cubic meter, a temperature 5 degrees Fahrenheit, 8 degrees Celsius. They're all 5 miles per hour, a height of 10 feet or 10 meters. They're all examples of a scalar. And again, that scalar is defined as a number and a corresponding unit. But then a vector is the number and the unit in addition to the direction. So that's a really big deal. And one example is displacement. We went, the hurricane came through and it picked your house up and carried it 10 feet north. So we know it carried it 10 feet away, but here the vector gives us the direction. We know it's specifically 10 feet north, not 10 feet south. Similarly, the velocity of a car is 5 miles per hour, and in the northerly direction. You're traveling 5 miles an hour north, or 5 miles, or in the example here, the picture, 25 miles, 25 meters per second in the positive direction, or you could say negative 25 meters per second, and the negative indicates that you're traveling in the negative direction. So it gives the context. It gives the minus sign indicates motion's negative, plus sign indicates it's positive. You'll learn that part in the upcoming chapters. So for now, what we really want to remember is that a scalar is a number along with its corresponding unit, and the vector is the number, the unit, and the direction. And then magnitude, velocity. Velocity and speed are related. Speed is the magnitude. The absolute value, speed is the absolute value of the velocity. So the way that's written, v is our vector, and the vector has that little arrowhead over it. And then the magnitude of that is equal to our v. Sometimes we can say it this way, as it's shown there too. So those little pipes there indicate magnitude. So how do you solve problems in physics? Well, we know that when we want to cook something, no recipe works all the time, but there's a general guideline to follow. Sometimes the recipe turns out fabulous, other times it don't, but we're not really sure why. But the recipe gives us a replicable, and that's a key thing. You want to be able to duplicate your work. And so the same thing here with solving a physics problem. Of course, you want to read the problem carefully and then sketch it out, draw what it's telling you, and then visualize the physical process. Try and visualize what they're saying. And then your strategy is going to be able to, a good strategy here is to write down the things you know, write down what you don't know, put a little question mark. If they say, if you don't know the velocity, but it's part of the equation, put a little question mark next to the velocity symbol. And identify your equations, solve them, and then double check your answer and ask if there's any limits or special cases. So number 8, we won't be really focusing that much on this semester, but all these steps are going to come into play in the next chapter and every chapter until the end of the year, until you finish Physics 2. So you don't have to really memorize these. Just keep them handy as we go through problems, and you'll see our strategy, and it'll become more clear to you as you solve the problems. So as we begin problem solving, that little list will be much more helpful. So here's a summary. Every one of our chapters, we begin with an outline, and there's a little bit of a summary at the end. Again, use that outline to help you study, to help you remember things. And then, of course, you can refer back to the chapter summary as well. One word of caution, do not make the mistake of only studying the summary. If you only study the summary, you're not going to pass. Of course, again, when you're home and you're taking the exam at home, it's still a timed exam, but at least you'll have the benefit of having your notes available. Preferably, we hope that you would try to take the exam without the use of your notes, because the more you study now, the easier your prep is going to be for that MCAT. So try to really make sure you understand all the concepts with physics. And of course, if you ever have any questions, reach out to me. So the lecture slides are what you want to study. And then when you go back to refresh your memory, use that outline to see how much you remember and what you need to study a little harder, which one of those topics you need to study a little harder until you master every one of them. And then, of course, the summary can also help you recall concepts. So we will see you next lecture, and thank you.